Hi everyone! I'm going to open my presentation with a very simple question. How many of you have been uncertain about the future at least once in your life? I can't see your answers, so backed up by statistics, I'm going to guess a lot of you. Well, we all need to face uncertainty at some point, future uncertainty, whether we're making financial plans, career plans, life plans. So every time we make decisions and plans, we need to account for variables that we don't know how they're going to evolve in the future. And much like our personal plans, we're forced to adapt to climate change, which also associates future uncertainties related to random natural variability, and then most importantly, to our lack of information and experience. When we talk about climate change adaptation of coastal communities, it is fundamental to know how coastlines are likely to evolve in the far future. And recent developments in numerical models provide us with reduced complexity shoreline models, which are capable to efficiently simulate shoreline change at timescales from hours to centuries. But unavoidably, these shoreline predictions are going to be affected by uncertainty. Currently, there's very little effort made towards understanding and reducing uncertainty related to wave-driven shoreline response. This is why, in collaboration with the French Geological Survey and the University of Bordeaux, we developed a framework to investigate the respective contributions of different sources of uncertainty to the uncertainty of the shoreline prediction. Today, I'll walk you through the application of this framework to the cross-shore-dominated Truc Vert beach on the southwest France, where we analyze the effects of uncertainty in sea level rise, depth of closure, and model-free parameters on a shoreline hindcast. All of this using a state-of-the-art numerical model and applying a global sensitivity analysis. First, I will briefly describe the application site and the numerical model, and then I will illustrate the method and our findings. The Truc Vert is an open wave-dominated sandy beach located on the Atlantic coast of France, and it's backed by a high and large sand dune. The local morphodynamics is mostly controlled by wave-driven currents, with negligible contribution of tidal currents. The site is exposed to a highly energetic wave climate, and the shoreline evolution is mostly controlled by cross-shore processes and shows strong interannual and seasonal variability. For our application, we use the Elixir shoreline model, which includes individual modules for wave propagation, cross-shore sediment transport, long-shore sediment transport, and sea level rise erosion. Given that the Truc Vert offshore bathymetry is fundamentally shore parallel, the breaking wave conditions in our application were calculated using the Larson's direct formula. And since the Truc Vert is known to be a cross-shore dominated site from the literature, in our application, the longshore sediment transport module was switched off. Sure, the cross-shore sediment transport module is an adaptation of the Shore4 model. Shore4 is an equilibrium shoreline model that computes the shoreline change rate in response to local wave climate as a function of the wave-driven hydrodynamic forcing at this equilibrium condition based on wave history and three model theory parameters that I marked in red on the slide. The C parameter is a response rate. It's basically a sort of efficiency for the shoreline erosion. The B parameter is an additional linear term that accounts for long-term effects of processes that are not explicitly included in the model. Finally, the phi parameter is a beach memory of past wave events. For the sea level rise response, Elixir adopts the Broom model, which computes the shoreline recession as a function of the sea level rise and the depth of closure. When predicting or hindcasting shoreline change, the uncertainty on the input variables will propagate through the model, producing uncertain results. In order to understand how stochastic input variables will affect the uncertainties of the results, we employ a variance-based global sensitivity analysis. In variance-based approaches, the uncertainty of a variable is measured by the variance of its associated probability distribution. The global sensitivity analysis, then, explores the entire range of variability of the uncertain inputs and of the model results in order to answer the question, how would the variance of the results change if I suddenly learn the true value of one of my input variables? Practically speaking, we propagate input uncertainty through the model by running an ensemble of simulations and obtaining a probabilistic estimate of modeled shoreline. We then decompose the variance of the output into several fractions, each one provoked by one uncertain input variable. We then use these fractions to estimate a sensitivity index known as first-order Sobol index, which allows us to rank the variables by the contribution that their uncertainties provide to the uncertainties of the result. For our case, the global sensitivity analysis required to define probability distributions for 5 uncertain input variables, which were depth of closure, sea level rise rate, and the 3 short-form model-free parameters. So we derived the depth of closure probability distribution by applying the Heller-Meyer formula over several portions of the available WIF data and fitted the results with a Gaussian curve. For sea level rise, we used the probabilistic estimate of past mean sea level obtained with a Bayesian approach, which resulted in a Gaussian distribution too. And finally, for the model-free parameters, we used shoreline observations, the short-form model, and an optimization algorithm to identify an ensemble of possible combinations of parameters, which gave a root mean square error lower than 10 meters over the calibration period. We then fitted this ensemble with an empirical joint probability distribution. Once we defined the inputs variable distributions, we ran an ensemble of 3,000 20-year-long simulations using different combinations of input parameters. And we obtained this distribution of a hindcast shoreline. The simulated shorelines show a similar behavior, and they have a notable spread in the long-term trend towards the past, and also in the amplitude of the interannual shoreline variability. The model also consistently reproduced the large erosion associated with the outstanding high-energy winter in 2013-2014, and the simulated shorelines are in line with the range of possible shoreline positions prior to 2011, which were data that were discarded from the calibration process because of their poor quality, but still provide a realistic estimate of the shoreline position. When we observe the results of the global sensitivity analysis, we see that the Sobol indices associated with sea level rise rate and depth of closure stay constantly under 1% throughout the whole simulation period, while the Sobol indices associated with the model-free parameters oscillate between 0 and 1 during the simulation. This shows that the impacts of the uncertainties of sea level rise and depth of closure do not emerge in the period object of this study. And this is not a surprise, because uncertainties associated with past sea level rise and depth of closure are relatively very small compared to model uncertainties. In addition, this result is consistent with previous studies which showed that the impact of the uncertainties in sea level rise will only emerge in the second half of the century. Instead, over the studied period, the model results are highly sensitive to the model-free parameters. The respective Sobol indices evolve rather gradually for the first 7 years of simulation in correspondence of a high variance of the model results, whereas in the remaining part of the modeled period, where the variance of the results is relatively small, we observe a large modulation, interannual modulation, and seasonal modulation of the Sobol indices. In particular, for the parameters C and Phi, we observe a clear seasonality of the Sobol indices, which suggests a strong relationship with the wave conditions. Instead, the uncertainties associated with the parameters B appear to have a large impact on the shoreline variance in long, low energy periods. So, to summarize our findings, we've seen that over the simulated 20 years period, the uncertainties related to sea level rise have basically no impact on the modeled shoreline. Then we've seen that improving shoreline models, for instance, explicitly including new processes that would replace the linear term B, would significantly reduce the uncertainties on the long term. Then we've seen that a better understanding of short-term processes would decrease the uncertainties on C, significantly reducing the uncertainties at seasonal scale. Finally, we've seen that the time distribution of wave energy is critical to the model-free parameters uncertainties. And this is important in the context of shoreline projections, because in some regions of the world, climate change will have a strong impact on the wave climate and extremes, in turn on the uncertainties related to the wave-related model parameters. And this would inject an additional component of uncertainty in the projections. If you want more details about our work, I refer you to our published article in ESPL early this year, and I invite you to ask as many questions as you want. Thank you to everyone for paying attention to this presentation, and enjoy the rest of the conference.